So everyone, I am Professor Marcos Santos, and I coordinate the activities on the Operational Research House. And today, we are going to learn about Newcomb-Benford law. Hello, Mr. Terra. How's it going?
Hello, Mr. Santos. I'm fine, and you?
Oh, I'm fine. Thanks for asking. Today, my guest is engineer Adilson Vilarinho Terra. He is an industrial engineer and works with operational research in the Brazilian Navy. He has several publications in the field of mathematical modeling. Thank you so much to accept my invitation to talk about Newcomb-Benford law. Mr. Terra, first talk a little bit about yourself, your studies, your family, your hobbies, and so on.
Hi, everyone. I'm so happy and so excited to be here in the Operational Research House. And I'm so excited to talk about the Newcomb-Benford law. That's amazing, amazing topic. And let's learn some how the Newcomb-Benford law can supply the decision-making process.
I think this law is
so important, no? For many things,
Exactly. We can apply this law in many totally different situations.
Yes.
To support decision making.
It can be applied in many different fields. Since volcanology, music, sports, soccer, etc. Healthcare.
Exactly. And where are you from? Brazil?
I'm from Brazil. I'm from Rio de Janeiro.
And where do you live? In Rio?
I live in Rio. I am an industrial engineer now.
Industrial engineer, yes.
At the Fluminense Federal University, located in Niterói, Rio de Janeiro. And I am 23 years old, and now actually I am at the Brazilian Navy as a mathematical and mathematical modeling.
Wonderful. And today we will talk about the Newcomb-Benford law, and we will try answer the question: when should I use this law? What kind of problems can I solve using this law? Right. So I think that recently you published a paper applying this law, right? Recently.
I didn't understand. Can you repeat, Master, please?
Recently, you wrote a paper, use Benford law, Newcomb-Benford law in data set about coronavirus.
Yes.
Isn't it?
Yes. Last month, the paper was launched at was published, and it's exactly this.
CMAP journal.
Yes. We take the data from our rolling data. We take the data about the COVID-19 numbers in Brazil, coronavirus in Brazil, and we take the number of deaths and the confirmed cases numbers in Brazil, and we analyzed this data
from the Newcomb-Benford law.
Yes. The optic of the Newcomb-Benford law.
And so we can analyze if we can believe in this data or no.
Yes, yes. And the results will show if we can use this data as a reliable database.
Okay, very good. So
to support the decision-making process, of course.
Well, make yourself at home and let's get started.
Let's go. I will share screen. One moment, please. So everyone, let's go. Let's talk about the Newcomb-Benford law. A numerical pattern that applies to classical music, social network, the fight against tax evasion, and perhaps even the universe as a whole. So it's a very complex law and a very interesting law. And I am completely fascinated about this law. So let's see a little more about this, the history of the law, these applications, and in the end, we'll talk about the paper. Okay. So the clue number one about the Newcomb-Benford law, what happens now? At the U.S. Naval Observatory Library, about 150 years ago, that's where the whole mystery began. Yeah, with a logbook, a logarithmic book from the late 19th century. The astronomer named Newcomb, who worked at the library in the U.S. Naval Observatory, he was checking out a book like this logarithmic book, and he noticed something a little weird, a little strange, no? What he noticed was that if you look at the front pages of the logarithmic book, you will see that they all are all the pages in the beginning of the book are all worn out. Yeah, but if you look at the page at the end, you will see that the wear is much less. Like people only use the first buttons on a calculator. Kind of random, right? Kind of strange. Newcomb think the same. So he looked at another logarithmic book and he found the same. So he was in shock, completely in shock. No? In all of them, in all books at he looked, always the first page spent and the last, always the first pages spent and the last practically new. So this is the clue number one. So what Newcomb realized was that the first clue of a deep and secret order to the world around us that can appear in everything, literally everything. No? Since your favorite sport, your favorite music, and even the way you are going to die. It's shocking, huh? It's a pattern that is everywhere around us. So let's go to the clue number two. Clue number two, Newcomb's discovery only began to gain importance more than a half century later with Benford, when physicist and engineering Frank Benford, that was born in 1938, incidentally came to the same conclusion that the same conclusion to the Newcomb conclusion.
That's why the law is Newcomb-Benford.
Exactly. So Benford published a seminal article, a seminal paper in 1938 called The Law of Anomalous Numbers, in which he used data collected from different types of sources. These data were random, okay, and had no relationship with each other. No relationship. He catch data from paper, data from number of houses in a city, random data, okay? And the range in numbers obtained on the main page of newspapers, as I talk, and the numbers of important readers did this topic to mathematical tables and scientific concepts. As I talk, random data, literally random data. So Benford's work, called the the Law of Anomalous Numbers, this paper, né? Benford work analyzed the first digits of the collected data and showed that about around 30% of the numbers had the first as the first digit, and that in contrast, less than 5% had the 9 as the first digit. So this is the clue number 2 of the Newcomb-Benford law. Benford noted that in the world exist less numbers starting with the digit 1 than numbers starting with the 9 digits, the digit 9. So this is a shocking discovery. Okay, so this discovery was gaining importance and was being disseminating around the world. And now exists a Benford's Law Conference, that is that's organized by the European Commission. That's a conference totally focused on the Benford Law. Okay.
I think many scientists studying Newcomb-Benford law all hold their lives.
Yes.
I think because we have many variations, many kinds, many different applications. Yes. So many scientists study only Newcomb-Benford law in all hold their lives, I think.
No doubt. It's a very complex law that can be applied in many different fields. So many science, including forensic science, are studying the law and are dedicating your lives to study the law. And the last conference occurred in 2019 in Stresa, Italy. Okay.
And many times we work with data. Many times we waste so much time to collect and organize our data set. So the math and expressions and law, I think they aren't so hard or so difficult. If you know the expression, if you know the law, it's okay. Like riding a motorcycle, you know, and okay, you know now and forever.
Yes.
But many times I see the problem is the data set. How can I get a good data set organized? And that's the big problem.
Yes, of course. To make a good decision, it's necessary to have a reliable database.
Exactly.
Right.
If you don't have good data, you have nothing.
Exactly, Master. So let's go. But in practice, what is Benford's law? What's the Newcomb-Benford's law? The Benford's law is the first digit phenomenon. Yeah? What happens? Imagine that you have a lot of random numbers between 1 and 999,000 to choose. Okay? Now choose a random number number in the bunch of random numbers. Okay. What will be the first digit of this number? What do you think? If it's a random number, it should be a random, right? It can be 5, it can be 7, it can be 1, it can be 4. Who knows? Can be random. The probability is the same, but it's not what happens. What happens is that there is a pattern, there is a standard. The chance of this number starting with the digit 1 is 30.1%, while the chances of starting with the digit 9 are less than 5%. These probabilities follow a logarithmic descending curve described in Benford's law. That is the curve showed in the screen. This beautiful curve is the Benford's law that states the in the world existing exactly 30.1% of the numbers starting with the digit 1, and less than 5% of the numbers starting with the digit 9. Okay, so this is the mathematical expression of the Benford's law. Yeah. Above we have the probability of occurrence of the first digit, the digit 1, and here we have as well we have the probability of occurrence of the second digit, the digit 2. Okay, that's a logarithmic descending curve, as I talked, and these mathematical expressions results in these tables, in these two tables. Yeah, that's as I talk is the probability of occurrence of the first digit and the second digit. So for the analyzing the first 30.1% of chance to catch a number randomly starting with the digit 1. We have the 17.61% of chance to catch a number starting with the digit 2, and as follows. And for digit 2, we have starting with 0, 11.7%, 11.38%, okay. Expected behavior first by the Newcomb-Benford's law. And for the second digit, now we have this curve to the expected behavior for the second digit by the Newcomb-Benford.
I think you are frozen. No? Hello, Mr. Terra? Are you hearing me? Hello? Hello? I'm not hearing.
Oh, sorry,
okay.
sorry, people. The connection is a little unstable.
Okay, no problem.
I will share screen again.
Let's go.
So you can see?
Yes. Who was talk about the second digit, Newcomb-Benford law?
Yes, the second digit.
More.
This is the curve, the expected behavior for the second digit expressed by the Newcomb-Benford law. This is the beautiful curve formed by the Newcomb-Benford law for the second digit. And as I talk, this is the behavior expected for the first digit.
First and second, okay.
Yes, perfect. Now, this is the first application that gain a big success.
Visibility.
A big visibility. Yes, perfect. So, what happens in Emerald Scandal? Mike Negrini, an accountant and an auditor, was one of the first to apply the Newcomb-Benford law as a lie detector. Okay, for detect reliable data. In 2000, he discovered adulterated accountants and at Enron Corporation, an American energy company located in Houston, Texas. The executives were pushing the bar and changing the numbers to look great, okay? Making up the records to achieve goals. So manipulating the data.
Okay.
The case gained a great notoriety in newspapers of the time, and company's executives were arrested. Now you can see the Houston Chronicle saying that the executives were really guilty to manipulate the data. Now we can see the results of the Negrini works. Now we can see the expected behavior in the first digit phenomenon in the Newcomb-Benford law.
Expected.
Now,
yes.
The expected behavior. Perfect. The expected behavior here, and now we have the fraudulent, the deviate pattern, the deviate from the pattern. Okay, and with these results, Negrini could confirm that really occur this manipulation of the data. So now we can see the first big case of the use of the Newcomb-Benford law as a lie detector. But it is only for tax. It can be applied only in accountants' data? No. Benford's law is much more than that. From here, we will see a lot of different fields that Benford law can be applied. The songs of Beethoven, Tchaikovsky, Bach, Schubert, all of them follow Benford's pattern, the Benford's law. Authors took the works of these musicians and measured the duration of each note, cumulatively throughout the work. Okay? By checking the first digit of these measurements, they found that it follows the Benford pattern, the Benford's law. It's a regular pattern that lurks behind the music of these artists. So the authors with this work, they comprovated that the Benford's law is applied in the classical music. Now,
very interesting.
No, it's very interesting. It's fascinating.
I see where you come from, because I think many people think. I think many people know Newcomb-Benford law, but they think we can apply only in financial crimes or things like that.
Financial data.
You know? Yes. But we have many other possibilities and totally different.
A lot of possibilities.
Wonderful. Go ahead.
So if we see the emergence of the Benford's law in music, now in this paper we have the comparison of the first digit frequencies in Beethoven's sonatas, notes, durations versus Benford distribution. Okay, it's a paper published by the researchers of the University of Chicago that that show us that the Benford's law can be applied in music, not only in financial data, in crimes data. It can be applied in much more fields. Okay, but the existence of a pattern surprise. After all, in accounting and in music, everything is a pattern, correct? Everything is a standard. But what happened if we apply the Newcomb-Benford law, where patterns shouldn't apply, where patterns shouldn't exist, okay? Where patterns should not exist. In sports, for example, in soccer, in basketball, in many sports, athletes do not want to maintain a pattern. They want to break them. They want to break the patterns. They want to superate even more. Okay. However, if we get sports statistics like basketball points, taekwondo kicks, number of touchdowns, numbers of passes in a soccer game, they all match the curve. The curve will always appear. They all match the Newcomb-Benford law. So it's amazing. So it's shocking to note that. So let's see this paper. That's a preliminary study to detect match fixing. Benford's law in badminton rally data. So it's a study that applied the Newcomb-Benford law in badminton. So the study verifies whether the number of rallies, universal and anomalous badminton matches follows the Benford's law. And the results shows that the match really follows the Benford's law. Okay? So it's fascinating.
It's phenomenal. It's amazing.
It's really incredible. I'm in love with the Newcomb-Benford law. So, does Benford's law apply to everyone? To all of us? Let's see. City populations also follow Benford's law. I catch the data about the population of all 28,339 cities, and I noted that all of them follows the Newcomb-Benford law. I catch the data from the simple maps, that is an interactive maps and database, and the result is the curve showing the screen. The population of all of the U.S. cities follow the Benford's law, and as you can see,
we can use this law in Brazil. We have 5,000 cities, so we can catch the data in IBGE and verify that the numbers works well in Newcomb-Benford law.
Yes, we can make this study.
Public data, everybody has.
Data.
Okay.
Reliable data, no? It should be. At least should be.
Right. So, write this observation. 5,000 cities in Brazil with population of the 5,000 cities.
Let's make this study.
Okay.
To check. Okay. So continuing. But it's a little intriguing. Why this pattern happens? Okay. Why? Because the population of a city seems like a number. Seems only a number. But
random number.
A random number. But it's not. It is a set of millions of highly personal decisions. All families can have
one kid. Oh no,
yes.
I don't
want to move to another city. Or no, I have a cancer. People die. So
I can't understand how how this equation works. I can't understand.
The nature is beautiful. So the population of cities are not random. It's shocking.
Yeah.
Even if some things seem random, they are not. The US crime figures, cancer rates, infectious disease cases, and even heart rates interval before going into cardiac arrest follow Benford's law. So here we can see a paper published in Geophysical Research Letters, yes, of the Benford's law in the natural science. Okay, so it's amazing. The Benford's law is really amazing. And now you can see as well a paper that applies the Benford's law in public health. It's from the Public Health Journal. No? It's a study of a global performance of epidemiologic surveillance of Zika virus, rapid assessment of an ongoing epidemic. So here is a case in that the Benford's law was used to measure the quality of epidemiological surveillance systems of Zika virus. And the results show that only 10 systems have adapted to the law. So we can apply the Newcomb-Benford law to check coronavirus databases, for example. In this paper was used to check the Zika virus database. So to apply the Newcomb-Benford law to check database the coronavirus database was the purpose of our paper published in the in the journal, in the paper. Sorry. So here continuing, we have the Benford law applying public health. No? Now this paper, this is used to measure the quality of cancer databases. So this paper is using the Benford's law as a first step to assess the quality of the cancer registry data. Okay, so the Benford's law can be applied in the public health as well. It's one more different field that the Newcomb-Benford law can be applied. One more field that the Benford law can be applied is in the elections. Okay, so the presidential elections, the government election. So the Benford's law in this paper were used to detect electoral fraud and irregularities in voting counts. So here we have in the left we have the detection by using the Newcomb-Benford law of the applications in the electoral process of the USA, Puerto Rico, and Venezuela. And in the right, we have one paper that was published in the electoral studies that checked the election fraud, digit tests, and how humans fabricate vote counts. No? This is an experimental approach. So the Newcomb-Benford law can be applied in the election as well. So the Newcomb-Benford law can protect the human being, the society as a whole, from various threats. It's also possible to detect fraud not only in the elections but in social networks too. By checking data from Facebook, Twitter, and Pinterest, the researcher Jennifer Gobeck of the University of Maryland found that the number of users of these networks follow the Newcomb-Benford's law. However, when analyzing a sample of 50,000 random Twitter's users, she realized that 100 of them did not follow the law. But so why? What this means? What this mean? So taking advantage of Twitter was public. data of Twitter are public, actually, she investigated these users that that not follow the law, and he found out that all of them were Russian bots operated by the same person. And what it's shocking, huh? And while continue her research, he found about 150,000 bots on these networks. So it's a threat now for all of the users of these social networks, the bots operated by the same person. And these bots can also influence in the election process in in really many cases. So it's a threat from the of the society, no? And Benford's law can really protect the society of these threats. Now we have a paper of the Benford's law applied on the social networks. No? The paper of Jennifer Goldbeck, and that shows that the Benford's law, the curve applied on these different social networks, Twitter, Google Plus, Facebook, and etc. Okay, see, so it's one more field that the Benford's law is used, the social networks. But it is possible to go beyond the identification of bots. What can we do with the Newcomb-Benford law? You can see when you can see when the bots, no, actually the bots post fake images, so we can look to the image and see if they are fake or not. How this is made? If an image is compressed into JPEG, its hidden representation follows Benford's law. Okay, if someone changes the image in Photoshop and saves it, it will undergo a new compression. It will pass through a new compression. And with this, Benford's law was raped. Benford's law does not apply no more. So journalists, courts, and intelligence agencies have used Benford's law to distinguish real and fake images. Okay? It's one more power. It's the power of the Benford's law to help to detect fake and real images. Maybe nature is governed by Benford's law. What do you think? We can apply Benford's law as well in volcanology. It's necessary in volcanology to predict assertively when eruptions will occur. Okay, we need to predict this eruption and to avoid it. Okay, however, this is not an easy task. It's difficult. What happens is that the human being began to monitor seismic activities about 3 decades ago, which in geological terms is nothing. Okay, we still don't have enough data to prepare after all geology. Sorry. We still do not have enough data to prepare to predict exactly when the eruptions will occur. After all, geology are numbers, are about numbers. Geology are numbers. So, with the imminent risk of volcanoes, the numbers better be right. Okay, we need to have the reliable data to predict when the eruptions will occur. So in volcanology, mathematical tools are being used to help see if the numbers are correct or not. The Barcelona Institute of Earth Sciences has used the Benford's law to verify that its databases are reliable and complete. So here in the right, we have a study of applying the Benford's law to volcanology, published published by the Gaia research. And now we have aquí the results of this paper. Okay. So maybe the Benford's law exists in all of our planet. And what about galaxies? So if you measure the distance from the Earth to all galaxies, the first digits of this distance will follow the same pattern. The Benford's law can be applied in the distance between the Earth and all galaxies, all existent galaxies. Okay, and the scariest thing, what scares me, what scares me the most is the fact that it can be measured in light years, kilometers, yards, inches, meters, and etc. If you get all of the units of measure, the Benford's law applies every time, always. The Benford's law is applied in the distance of the Earth and all galaxies. So one more field that the Benford's law is being applied is astronomy. Now we have in the right we have a paper that investigates the applications of the Benford's law in astronomy, no? And in the left we have the paper that calculated the distance of the galaxy to the Earth and applied the Benford's law. So this is the results of the paper that constat really constat that the Benford's law is applied to the distance of the Earth to all galaxies. So really, there is a mathematical order in action that connects the whole world. That is an amazing mathematical order. Is an amazing mathematical pattern. So it can be applied in everywhere. Where you imagine the Benford's law can be applied. Okay? So checking the data on the Brazilian numbers about the coronavirus, no? The numbers of the total number of cases and deaths by coronavirus, the data reported in the media vehicles, we check if they are in line with the Benford's law. Okay, so we collected data from the Our World in Data database. That is a database of the Oxford University. Okay, so we collected data in the period of 26th of October and 26th of October in the 2020, 2020, and we catch the sorry, I'm little why how can I say, we catch data from February 26 February from 2020 and 26 October of 2021. Okay, sorry guys. Now we check if we can apply the Benford's law in the coronavirus data, in coronavirus Brazilian data. The confirmed cases of coronavirus in Brazil, as we can see, do not follow the Benford's law. It's not in line with the expected behavior in the Benford's law.
This fact is very important.
Yes.
You are not saying there is a data fraud. You are saying that there was no adherence to the Newcomb-Benford law.
Yes.
I think.
And
if there is fraud or no, I don't know. We need to study a little more.
Yes, yes.
But I can see there is no adherence in Newcomb-Benford law.
Yes.
It's clear to me.
Yes. The numbers do not lie.
Exactly.
By looking to this image, to this graph, we can see that really exists a little divergence by the expected behavior and the observed behavior in the data. So really have a divergence. Okay. So this is the confirmed cases of coronavirus in Brazil.
Yeah.
For the first digit, this is the analysis of the first digit. And now we have the analysis of the second digit. As well, do not follow the Benford's law. As the first digit, do not follow the Benford's law in the second digit. And looking to the total deaths, we see that do not follow as well. This is the analysis of the first digit, and here we have the analysis of the second digit. Do not match. No? They are not in line.
Come back one more slide.
Sorry. As you can see, they are not.
No adherence. No adherence.
Completely no adherence. In the beginning, we have that it's have a similarity, but really do not have adherence. No? And we will see this in the comparison frequency test, the chi-square test. Okay. So this is the Benford's law for the second digit in the total deaths. We see that they are not in line with the Benford's law. But we need to make a frequency comparison test. No? So we ask, is there a significant difference between the observed and the expected values? The difference observed is significant or no? To check this, we will use the chi-square statistic that's expressed by the equation below, this equation here. And with this equation, we can, with this test, the chi-square test, we can see if the difference are significant or not. Okay. But how does the chi-square test happens? The process of frequency comparison testing happens as follows. The expected frequencies are calculated based on a null hypothesis, the H0 hypothesis. Okay. If for this hypothesis, the calculated chi-square value is greater than the critical value given in table, it's a table number given in the table, we conclude that the observed frequencies differ significantly from those expected. And then we reject the null hypothesis at the corresponding significance level of 5%. Okay? Otherwise, we must accept the null hypothesis, or at least not reject. In the present study, we considered for the calculated chi-square the sum of the 9 possibilities of Benford's law in the first digit, and for the second digit, we consider the 10 possibilities of the law. So in that way, for the first digit, we have 9 possibilities, no? With the degree of freedom equal to 8. 9 minus 1 equal to 8. And for the second digit, we have 10 possibilities with a degree of freedom equal to 9. Okay, perfect. And for as I say, for critical chi-square, we set the significance level at 5%, which is the standard value used statistically. Okay, in statistics, the is very common to use the significance level at 5%.
The train of thoughts is very simple. We have to compare the result, the expected result, the difference between expected results and real results. It's very simple train of thoughts.
Perfect, master. And now the values considered for the first digit frequency comparison test and the values considered for the second digit frequency comparison test. For the first digit, as I say, we have a degree of freedom of h, and the critical p-square that's given in table is equal to 15.507.
And for the second, we can use another test. We can use another.
Perfect. You can use another test.
Is more simple.
Yes, you do have MAD tests. You have a lot of frequency comparison tests.
Yeah.
Okay. But in this study, we use the p-square test. That is largely used and is very common to be used in for this nature research.
This method works well.
Yes, work well with the Newcomb-Benford. Okay, and for the second digit, we have the degree of freedom equal to 9, and the critical p-square that is given in table is equal to 16.919. Okay. So for critical p-square, we set the significance level at 5%, as I say, which is the standard value using statistics, and we consider these two hypotheses. The null hypothesis states that there is no significant difference between the observed and the expected frequency, and we will reject this hypothesis if the calculated p-square be higher than the critical p-square. So the hypothesis H1 states that there is a significant difference between the observed and the expected frequency. Thus, to evaluate whether the hypothesis H0 was rejected or not, we compared the values of calculated p-square and critical p-square, allowing us to infer two options. These two options below, to reject or not reject the null hypothesis. Okay. So this is the result of the p-square, the p-square test applied in the number of Brazilian confirmed cases in the first digit. Now the results show that we hypothesized that there is a significant difference between the observed and the expected frequency of the number of confirmed cases at a significance level of 5%. As you can see, the calculated p-square is bigger than the critical p-square. Okay, so we reject the null hypothesis, and we assume that there is really exists a difference.
The difference is bigger
the
than
significant difference. The significant difference really exists. Okay, and for the second digit of the Brazilian confirmed cases, we see that really is a significant difference, because the calculated p-square is bigger than the p-square given in table.
Perfect.
Okay. Now for the number of deaths, analyzing the first digit, we have even a bigger difference. The calculated p-square is about
a huge difference.
a huge difference. And the p-square given in table is 15.507. So really have a
like we saw
difference.
the worst graph.
Yes.
Result this huge difference.
Yes.
Like we watched.
Yes, the expected values are the values observed are much higher than the expected values.
Exactly.
Of course, there is a significant difference. So
the numbers show what we saw.
Is exactly. The numbers show what we saw in the graph.
Exactly.
Now, for the second digit, is the unit that was that the critical Q-square is less is menor. Eu esqueci as palavras em inglês.
Less than.
I forget.
Less than.
Yeah. Is less than the critical Q-square. Okay. The calculated Q-square is 13.375, and the critical Q-square given in table is 16.919. So
okay.
There is not a significant difference in the second digit.
Yeah.
But in the first, we have a significant difference.
Okay.
So I'm so thankful, so grateful to talk about the Newcomb-Benford law. It's an amazing topic. It's a vast topic. It can be applied in many fields.
Wonderful.
And if we could, we would pass the whole world talking about the Newcomb-Benford law. So thank you one more time, and
congratulations.
I'm here for
congrats for our research. It's a wonderful research.
Thanks.
And I think many people can ask me, Professor, where can I apply Newcomb-Benford law in operational research? Newcomb-Benford law, can I consider like a subject from operational research? And I think, sure, of course, you can consider, because in operational research, we work with mathematical models to support decision making. But to use this model, I need a data set. And I need to trust in this data set. So we can use the Newcomb-Benford law in any data set to verify if I can believe it or no. I think. Like this case about coronavirus in your research, how can I plan up, how can I say, how can I plan a public health policy if I can't trust the data?
Impossible.
So I need first trust in the data, and after that I can apply another methods, another approaches to to figure out the solution.
Yeah.
You know?
I think that the first step to have a good decision process, to make better decisions, is to have reliable data. I need to trust in my data.
Exactly.
Because if the data are wrong, are not
you have nothing.
Trustful. I have nothing.
You have enough.
So the first step to make a good decision, to make better decisions, is to have reliable data. Without the reliable data, we have nothing.
Okay, thanks so much for your presentation. it was an honor for us to have you here today. And we have many others like the class today. We have many other classes in our YouTube channel, and we have almost 400 classes about Kruskal algorithm, trivial salesman problem, simplex method, analytic hierarchy process, and many other methods we have explained step by step. So if you want to learn more about operational research, you are invited to visit our YouTube channel. And Adilson, one more time, thank you very much for your presentation. And Happy New Year.
Thank you very much, Master. It's an honor for me to share my time, to share the knowledge, to talk about sciences, to talk about the Newcomb-Benford law. So it's a pleasure for me to be here in the Operational Research House. And one more time, thank you and Happy New Year.
Happy New Year. See ya.
See you.